Thank you, Frederick. And I would also like to thank all the organizers for such wonderful events. And also, I would like to thank Pascal for the opportunity to do my thesis at OSI 14 years ago. So, along these years, what I have been working on a lot, always very close to Pascal's work. But somehow all this what I have done is related or motivated with so the PhD thesis topic, which is about the LP boundaryless of Riesz transform on fractal-like manifolds or graphs. And today what I'm going to talk on is still related to this topic. So I will discuss about gradient bonds for the heat color on the Vicsek side, which is a real fractal, but the simplest, maybe. So I want to start with gradient estimate for the heat color in the general smooth structure, so which is related to the like Riemannian manifolds satisfying Gaussian heat color bonds. So this gradient bond has been extensively studied since the 1980s. And there are many different interpretations of the gradient bonds depends on the geometric condition. So for instance, it can be a pointwise estimate, so for which here compared with this heat color bond, which can be both up and lower bound with different constant C. So in this pointwise gradient bond, there is an actual square root T. So also we may understand it as the LP gradient bond. When I mean LP, this P is between 1 and infinity, including infinity. Of course, as P increases, so this condition is stronger and stronger. So when P equals infinity, sometimes we call it Vickers-Becquerel-Emery estimate, which is also equivalent to the pointwise estimate here when the setting satisfies doubling condition. And the last one is the LP-LQ of diagonal estimate, which is more common, like for operators, the heat color, so the heat saving group associated with elliptic operators of divergence form. So, okay, and another thing I will also talk about is the Poincare inequalities. So we have seen Poincare inequalities in many different places. Generally, so it has this form for PQ between 1 and infinity. So P is less or equal than Q. So we are more familiar with the following form, which is this L2 Poincare inequality. In fact, Euclidean space or Riemannian manifolds with line-negative or Riesz curvature, so the LP bond, the LP Poincare inequality for P equals 1 is also true. So what I will discuss today is about essentially these two topics, fractals. So the most interesting motivation or application that I'm concerned is the application to study the LP boundaryless of a Riesz transform, or more generally, the comparison of the two semi-rooms of Sobolev space. One is through the local gradient. Another one is through the global Laplace operator. When I mention Laplace operator, it's always the non-negative Laplace operator. So as I said, it's a generalization of the Riesz transform. So when I talk about the LP boundaryless of Riesz transform, it's this relation. And also, we are also interested in the reverse inequality, which we call it the LP boundaryless of reverse Riesz transform. Okay. So by duality, the Riesz transform implies the LP prime boundaryless of the reverse Riesz transform, where P prime is the conjugate of P. Of course, so this study of the application for the gradient bound of heat colors and the Poincare inequality to derive the this relation EP or P prime. It was done in these two influential papers by Pascal with other co-authors here. Steve is also here. So in the first paper, so simply speaking, so there is a new criteria was established to prove the LP boundaryless for very general operators in very general setting. So for P larger than 2. So the main result is that if this setting satisfies volume doubling property, and the L2 Poincare inequality, which I showed before, and the LP0 gradient bound of the heat color. So for which this P0 is larger than 2. So then we have the LP boundaryless of a Riesz transform for P between 1 and P0. In the second paper, it's more about a direct proof to derive the LP boundaryless of reverse Riesz transform. Where Cardinal-Zygmunt decomposition for Sobolev spaces was established there. So if we have a doubling and L2 Poincare inequality, so then the reverse Riesz transform is true for some Q for P between Q and 2. So it will implies the comparison for both sides for P between Q and Q prime. So there exists some Q less than 2 here. And of course, if we have L1 Pangara inequality, so then we can derive EP for P between 1 and 2 plus epsilon for some epsilon larger than 0.
Sorry, what is Q in your statement?
For some Q less than 2, there exists some Q. Yeah. Okay. So with this motivation in mind, so we want to know what is Riesz transform on fractals. So here is a picture of this Vicsek set, which is, you can see it has both the tree structure and the fractal structure, right? So then, in order to study the gradient bounds, Sobolev functions or Sobolev inequalities, Pangara inequalities. So then we wanted to know, like, what's the analog of this thing, or we can consider either on the Hall space or on a set. So, so that's the first thing we want to understand, to keep it in mind. Okay. So, and as we can see, so there is the at least the obvious analog of curvature or differential structure. So then that's we are going to study what's the appropriate differential structure here. So before I continue, I want to mention two relevant results for which we study Vicsek manifold or graphs, which is not directly Vicsek set. So the difference here is that we consider, so that's like a part of the Vicsek graph. So then there are vertices and edges. Each edges, it's like has distance 1, has length 1. And what's the Vicsek manifold? So the Vicsek manifold is that we replace each edge by a cylinder, and we glue them smoothly at the vertices. Okay. So then what I proved with Joseph and Emmanuel here, and also with Thierry Coulomb, is that on such setting, so the Riesz transform holds if and only if P is between 1 and 2. And the reverse Riesz transform holds if and only if P is larger or equal than 2. Well, so here, because it's manifold and the graph, we do have a gradient, or at least for the graph, it would be a discrete gradient. Okay, so that makes the analysis much easier in some sense, although it's still not easy. And I also want to mention some recent work of Baptiste Emmanuel here, and so what they work on is the Vicsek cable system. So for the Vicsek cable system, we also, for each edge, we also consider all the points on the edge. We don't only regard them as a line collecting two vertices. Okay, So then what Emmanuel and Baptiste they proved very recently is that the reverse quasi-Riesz transform holds. So there is some gamma for some p star. So whenever gamma is in this range and p is larger than some p star, for which this p star, it depends on gamma, on p, and also on the volume of, on the dimension for the volume. And it's false for p less than p star. Okay. So that's some recent results. So it's very interesting and motivated us to think about the real fractal case. So of course, I only mentioned the result of Riesz transform, but in the proofs, so the gradient bounds for the heat color is K ingredient in both these results. Okay. And then I will discuss a little bit background about the study on fractals. So in the early 1980s or before, so it's mostly math physicists study the diffusion on fractals. It's not on real fractals, but random walks on fractal-like graphs. So then people started to study analysis regularly on true fractals, like Sierpinski cascade, which is the most well-known, and I will give you the picture in the next slides. From the later 1980s and afterwards, so then there has been many studies about the heat colors, the heat semigroups, and the Pangar inequality, Halleck inequality, all these related topics are regular fractals like Sierpinski cascade, cavite. So there is a list of mathematicians who are working on that. It's a very partial list. Okay. Okay. So then the idea to study the fractals is to use heat color and a heat semigroup. So it will work nicely not only on the Vicsek set, but also Sierpinski cascade and Sierpinski cavite. But if we look carefully about the picture, so the cascade and cavite, they don't have tree structure. But the cavite is much more complicated than the cascade also, because if we look at the cascade, if we remove 2 points, so then the set becomes disconnected. But for the cavite, so we cannot make it disconnected by removing finitely many points. Okay. So that's why the analysis are much more complicated cavite than cascade. Okay. So finally, let me rigorously introduce the Vicsek set. So there are 5 contraction maples. So for which this Q1 to Q5, there are 4 colors and the center of the Euclid square. So we can think of the center as 0, 0. Okay. So we can look at this structure. Okay, so the Vicsek set, the compact Vicsek set, is a unique line empty compact set for which the set itself is the union of the 5 contractions of itself. Okay. And we can blow up the compact Vicsek set as in the picture of some slides before to a line compact Vicsek set. So for instance, if we set the center to be 0, 0, so then we will get a line compact Vicsek set for which we repeat the same structure on the diagonals. Okay, so also as I emphasized before, well, because the Vicsek set is simple, it has also the tree structure, so then the analysis would be more accessible, and we hope to get some inspiration or motivation to work on more general setting. So these slides are some notations. So, okay, maybe. So, well, one can approximate the Vicsek set by a sequence of Vicsek graphs, for which every time we do the contraction maps, when I write this capital Phi, it means the 5 contraction maps. So, okay, so like at the beginning we start from this one, then we do 5 contraction maps, we do 5 again, and so on and so forth. And of course, if we repeat the same structure on the diagonal, so then we obtain the unbounded case. So, okay. So as we can see that every time after we do the contraction, so then the length of the edge, it becomes 1/3 of the previous step. So then at the end, so if we do a completion of all this union, we get the Vicsek set. And then I will use this V overline to denote the cable system or the metric graph, which means we also count each point in the edges. So another very important thing that I want to introduce is if we do the union of all these metric graphs, we get a skeleton. It's still not the Vicsek set. As I said, we need to do a completion. So, but this skeleton is also very interesting for us because we can impose a length measure on the skeleton. Okay, because so which is a very less measure. It's sigma finite. So in order to do analysis, so now we want to know what's the measure, what's the distance, what's the energy form. So here, so we use mu to denote the Hausdorff dimension, and d is the Euclidean distance. Sometimes people also think of the geodesic distance. So then, with respect to this Hausdorff measure, so its alphas are regular, and with Hausdorff dimension dh, which is log 5 over log 3, and it's not very difficult to get this number because every time we do the contraction, the diameter we get is 1/3. And every time we get like 5 contractions. So that's log 5 over log 3. The next thing is about the energy measure. So it's a strongly local regular Dirichlet form. It can be approximated from the energy form on the graph. Okay, so here there is extra 3a. It depends on the structure of the Vicsek set, or the resistance scale constant. Okay, so that's on the compact case. Of course, it's well studied that one can extend this Dirichlet form to the non-compact case through dilation and limiting procedure. So there exists a measure with respect to this Dirichlet form in the sense of Bernoulli. So the very special thing on the fractal is that such energy measure is not absolutely continuous with respect to Hausdorff measures. This means we don't have the Gahe-Duchamp. Associated with the energy measure, so there is also a Laplace operator and a Hit semigroup. So this correspondence is 1-to-1. So on the Vicsek side, so it was proved by probabilists using probabilistic potential theory that it satisfies the sub-Gaussian heat-color bonds. So when I mean sub-Gaussian, on the Vicsek case, dW is dH plus 1. So it's log 15 over log 3. So it's a number strictly larger than 2. So of course, if dW equals 2, it's the Gaussian case. So, and in general, so on fractals, this dW is larger than 2 and less or equal than dH plus 1. This means on the Vicsek set, it's the borderline case. So the L2 Pangara inequality is also known. Instead of R2, R square in the usual case, so here it's R dW. dW is strictly larger than 2. Okay. So that's what we know for this, for the Vicsek set, or even for more general like Sierpinski gasket cavite. Okay. With all these preparations, so then we are getting closer to understand the analog of these objects here. So we want to know the p-energy for some sense. So there has been many studies for Sobolev spaces from these different perspectives on metric measure space. So for instance, there is Caroversian space, Hawash Sobolev space, Pangai Sobolev space, and on the fractal settings, so it was studied also in a paper by Jiaxin Hu in 2003 and by Piachuska, Paluba, and Stoss about 10 years ago. So, and so there are more recent studies. So in a series of papers with many co-authors, we study this heat color based base of space, and also very recently, so there has been many studies using the discrete p-allergies. So the first paper I wrote, maybe this one 20 years ago, and then there are many recent works in the last 5 years. So I will discuss what are the appropriate Sobolev spaces in our setting. So the first thing we are considering is the Carl-Version Sobolev space. So okay, so there is this notation. I write it as EP alpha F R. So for a function f in LP, and R is any positive numbers. So okay, so the Carl-Version Sobolev space in our case it's the functions f in LP such that the name soup of this object is finite. Actually, so this alpha here is 1 plus dh minus 1 over p. So, okay, because of the special relation that dw equals dh plus 1, so then we can also write it in terms of dw. Okay, so here this p is the critical point, so that this space is not trivial in the sense that not all the functions are constant. Okay, so then one can consider this Carl-Version semi-norm. So compared with the usual base of Lipschitz norm or semi-norm, so then here we use limit soup instead of soup. So so that's one viewpoint towards the Sobolev space. Okay, so it's purely a metric definition. And the second one is about the discrete approximation. So if we are consider a less collected subset, so then one can consider the p-allergy measure on the Vicsek graph in this way. So here this 3 is the same as the dirichlet form, but the power of 3 is adapted to the LP case. Okay. So then one can define the LP allergy form as so the limit and have a Sobolev space where the p-allergies, so for which the Sobolev semi-norms in this way is so here there is power 1 over P because we want to do analog of the LP law. Okay. And still one other. So it's what we call, we introduce a so-called weak gradient. So of course it looks a little bit messy here. So okay, so we consider any fixed n for all the possible n. So then in each level, so there are edges and vertices. So now we consider two labeling vertices. So then for every function at two labeling vertices, so we can write it in this way. So, so that's for all level n. Of course, we need to set an order of V and U different vertices, but because of the tree structure, it's relatively simple. We can fix the center, like at 0, 0, then we count the distance of each vertices to the center. So they are all not the same for two labeling ones. So then we can fix an order of it. So, so then one can define a Sobolev space where this weak gradient. But so there is a typo here, and okay, so it should be on the skeleton. So as we introduced before, so this is only possible if we consider the skeleton, not all the part in the Vicsek set. Okay, so then let's just consider the skeleton. And then, so here X is S, okay? And the measure is the length measure. It's not the Hausdorff measure. So, so in a joint work with Fabrice Baudouin, so we proved that all these spaces, they are equivalent. And also, their simulons are comparable. So, okay, so I will not show you the proofs, but I want to give you maybe some key ideas why it works well on the Vicsek set. Actually, it may not work well on the Sierpinski gasket. So, so one important ingredient is the existence of such quad and piecewise affine functions. Okay, so it means, so if it's n piecewise, so for example, if we look this picture here, it's if we want to consider two piecewise function, it means so the values on the edges, they are linear with respect to the two labeling edges, the value of the function. And for all the other components, so that's what we look at this picture here. So then we want to consider the other level, right? So if we repeat the structure, okay. Maybe it's better that we consider one piecewise picture and then to go to two. So the picture is easier. So this means, okay, so we have 5 points, right? So we have two diagonal lines. And so we fix the value on the vertices, and between the two vertices, it's linear function. So then to the other level, so all these actual lines, their value is the same as the point on the diagonal, and further levels. Okay. So that's what we call piecewise affine functions. So this function has very nice property, and also because of the structure. So actually, if n is larger or equal than m, so then EPn and EPm, they are the same. So it will stop glowing. And for each continuous function, we can approximate it with a sequence of n piecewise affine functions, which means we take Hn(f), we take the same value at the vertices of the n level, and then so f can be approximated by Hn(f). And also, the set of compactly supported piecewise affine function is the cone of the Dirichlet form. Actually, the Dirichlet form, we can also consider that the domain is actually W1, 2. So this means we have a very good simple test functions. Okay. So that's the piecewise functions. And another key ingredient is the Mori type estimate. So the Mori type estimate, when I write a convex set, it means so this set is a collected set. So then one can easily obtain this estimate if x and y they are vertices, and otherwise by approximation. Actually, so this estimate can be obtained by simple Herder inequalities. Okay, and from the Mori type estimate, so we can also obtain the LP Pangara inequalities. So it's not difficult to see that we can go from Mori inequality to Pangara inequality. So here we get, so that's for all p between 1 and infinity. So I will not mention specifically p equals 1 because it's sort of another story. So, okay, so here the parameter here is p minus 1 plus the edge when p equals 2 is indeed dw. Okay. So now with, as we have already understand the Sobolev spaces in a few different ways, so we can try to prove some gradient estimates for the heat color. So the gradient estimate here we obtain is for the weak gradient that I introduced before. So, so here I want to mention that. So that's for. So I said almost mu almost everywhere x in S. So then the set of x depends on y. So it's interesting to know whether it's independent from the choice of y. Okay. So there are two results here. So one is about the pointwise estimate. So C over T1 over dW, PCT. Actually, so this it's not surprising because this 1 over dW, if in the Gaussian case, we can correspond it to square root T 1 over 2. Okay. And another result is about the gradient, the LP-LQ bond. So here, so again, so in the left-hand side and the right-hand side, it's not about the same space, the same measure. Okay, and in particular, if P equals Q, so there is a type it's LP. So then we can see that this alpha P is 1 minus 2 over P times 1 over dW plus 1 over P. So that's so this parameter here, it's related to the parameter in the Poincare inequality. It's that parameter over dW here. Okay. Next, I want to discuss still some ideas for the proof of such estimate. So actually, from the work of Martin Baller, still through the probabilistic potential theory, then what he proved is from his method, we can prove such Herd continuity for the resolvent curler, which is the curler for the resolvent operator. Okay. So this is a very less estimate, and then if we work harder, so applying semi-group properties and sub-Gaussian heat curler bonds, then at the end we can derive this Herd regularity of the heat curler, or in this case, actually it's Lipschitz because the power of dxy is 1. And then because of our notion of a weak gradient, so we can get the pointwise bound, but it depends on y, as I said. And for the integral estimate, because it's two different P spaces, so then it's not a direct consequence from the pointwise estimate. So instead, we need to prove so this kind of integral estimate with respect to the length measure nu on the skeleton. So the idea is to introduce a co-differential operator so that the Laplacian can be written as the delta star, the partial star and partial u. Okay. So this co-differential operator is adjoint of the weak gradient I introduced before. So then, well, because so then thanks to the and piecewise functions, so at the end, so we are able to prove such estimate if we plug in the weak gradient of the heat curler, then we get the Laplacian on the heat curler. So then we can again use the analyticity of the heat semigroup to obtain the result. Okay. So that's the gradient bond and the Pangaea inequality I want to introduce, and the following are some applications, mostly Sobolev flash type inequalities. So the first one I want to introduce is this LP pseudo-Pangaea inequality with respect to the heat semigroup. So we can prove this Pangaea inequality. This alpha p is the index from the ingredient gradient bonds. So, and actually, so this Sobolev semi-rule, in terms of the weak gradient, it behaves very well under cutoff functions. So, like, so in the first one, T as a positive constant. The second one, rho is a number larger than 1. Okay, so then one can apply the very general theory developed in the paper by Bakri, Coulomb, Ledoux, Salovkast, paper called Sobolev inequalities in disguise. So we can show the following large inequalities. So still, we always have two different Lebesgue spaces. And so the other inequalities I want to introduce is the following. So this alpha p is still the same as before. So,
Can you repeat what it was?
Okay, I can write it here. So alpha p is 1 minus 2 over p 1 over dw plus 1 over p. So when p equals 2, it's 1/2. Well, so there are two inequalities we can obtain. So well, it looks complicated. So there are S alpha p. Okay, so then that's the power S fractional Laplacian here. So the first one, it says if S is less than alpha p, so this is 1 minus S over alpha p, so here it's S over alpha p. So the second one is when p larger or equal than 1 and S is larger than alpha p. So in this case, alpha p over S is less than 1. It's some special theta. Okay, so why am I interested in this inequalities? Because if in the borderline case, critical case, for example, if S equals alpha p, so then so if S equals alpha p, we can see this term disappeared, right? And for the second one, so it's this term disappeared. So this is sort of look like the LP boundary list of Riesz transform and the LP boundary list of reverse Riesz transform, right? So that's the conjecture we have. So then we think on the fractals for the Riesz transform. So this alpha p, it depends on p and the geometry of the fractal. And so this conjecture also coincides with the conjecture in the paper of Baptiste and Emmanuel. So for the Vicsek cable systems. Okay. I think it's time to stop here. Thank you. And je l'anniversaire, Pascal.